tienes todo el tiempo del mundo. Gracias.
Muchas gracias. Buenos días a todos. Primero, muchas gracias a los organizadores por la invitación. Entonces, hoy tengo 40 minutos para hablarles de 20.000 años de evolución. Entonces, vamos a ir rapidito. Es un review, entonces les voy a hablar de lo que sabemos y sobre todo lo que no sabemos. Entonces, vamos. Ok, entonces el outline de esta plática es muy simple. Como lo dice mi título, vamos a hablar de diferentes fases. Solamente les voy a hablar de estrellas de masa intermedia, entonces entre 0,8 y 8 masas solares. Vamos a ver la fase de Post-AGB, vamos a ver las nebulosas planetarias, las enanas blancas y las estrellas centrales de nebulosas planetarias. Vamos a ver lo que llamo la familia extendida y terminaremos con el campo de las estrellas evolucionadas en México. Y ahora voy a cambiar de idioma para ir aún más rápido. Okay, so post-AGB stars. So what do we call post-AGB star? What's happening during post-AGB stars? So basically, this is the phase after the AGB, as the name indicates. So during the AGB, you have lots of mass loss between up to 10 to the minus 4 solar masses per year. They are characterized by a large infrared excess, mid-infrared excess, and basically they are transitioning to higher temperature. The temperature of post-AGB stars generally it's around up to 7,000 to 8,000 K. So those are classified as cool objects. So the main point of post-AGB star is that they are not hot enough. At 7,000 K, you're not hot enough to ionize all your nebulae. So generally, we find two types of objects, the one that are totally exposed. So here, for example, in 89R, you can see the central stars, and you have another family of objects that are totally embedded in dust. So you're not seeing the central stars. So what has been done during the last 5-6 years in the field? So I did an IDS search, and those are the keywords. So they've been working on outflow, on envelope, on the abundances, the nucleosynthesis mostly, the detection of objects, their envelope, their disk, and as well as objects like asteroids and planets. So we're going to go through some of those topics. So first of all, what are the open questions? So there's a lot there. So just to show you everything that we're working on in that field. So we're going to go one after the other. First, we're going to see the mass loss. So basically, we want to know what characterizes and what drives the mass loss in AGB stars. AGB and post-AGB stars. Basically, how the mass loss produced during AGB stars will affect the second stage. Then we have the chemical abundances. Chemical abundances, very important because we want to know what is the composition, the abundance of post-AGB stars. So we will be able to investigate processes like nucleosynthesis. Then we have the evolutionary paths. How post-AGB stars evolve? Do they all evolve on the same path that we've seen in the HR diagram? Or we have or we have really different way of going through the post-AGB stars, depending on some factors that we don't know yet. Then we have the circumstellar environment. As I said, those objects, some of those objects have large circumstellar envelope. So we need to understand, for example, the shaping of those envelopes. Basically, and we will see that in a minute, what drives the non-spherical shape of some of those post-AGB stars. What are the main factors? We have the final states. Do all post-AGB stars end up as planetary nebulae, which then end up as just a white dwarf? So we've seen that not all follow that path. So that will be something very interesting to study. Then we have the formation of dust grains. In those circumstellar envelope, you have the perfect condition to form a lot of types of dust grains. So those dust grains are really important to understand when you want, for example, to calculate the mass, the ionas, not the ionis, when you have to put the molecular mass and the molecular mass, and the dust mass. The binary interaction. We will see in a minute that a lot of the post-AGB stars have been detected in a binary system. How the binary system influence actually all these other parameters, because everything, you'll see that everything is linked. Then we have the connection to exoplanets. So this is very recent. So we will try to see how planets can connect and can fit in all that designs. Okay, so first we're going to start with the sample. The first thing you have to do is to know how many post-AGBs you have. So if you're looking for post-AGB, the way to go is here. The Torun catalog for galactic post-AGB by Sherba. So this is all, an implemented database where you have all the the galactic post-AGBs that are known so far. So in that catalog, we have 209 likely and 87 possible post-AGB stars. The interesting fact, like I showed you at the beginning, is that you have in post-AGBs is that you can be able to have data on the central star and the shell. Here you have, for example, two diagrams by Kamat and Van Winkel in 2022, where they show you 6 different post-AGB stars. So on the top, the top row, you have what they call shell post-AGB stars. And on the bottom row, you have what they call disk post-AGB stars. What's the difference? The difference is on temperature. So the shell type, they have cold and detached expanding dust shells. The disk type, they have hot dust circumstellar disk. So generally, the top one, the shell post-AGB stars, they are linked to single post-AGB stars. The other one, the disk type, they are linked to binary post-AGB stars. And also something that has been very important is Gaia. The fact that we have good distances and the luminosities, so we can have more and more information, for example, on initial mass and final mass, etc. We were talking about disk. Why are we interested in disk in post-AGB stars? Well, most of the AGB, they are kind of spherical. But when you look at most of the post-AGBs, they are not. So how do we go from there to there? So basically, it's a combination of ingredients. So first of all, we have a post-AGB with a rotating disk. Generally, it's a Keplerian disk. In a binary system, you have the presence of an accretion disk and jet launching. If you have those 3 ingredients, then you will be able to have this type of shape. So people have been looking for those disks. So there was plenty of theoretical work stating that we need all those 3 ingredients to have those non-spherical shape. So we were looking effectively for disk. So there's the work for Bujarabal in 2013 and his team. They have been detecting a lot of Keplerian rotating disk around post-AGB stars. So here you have all the different CO profiles. So in red here, those are the models. Sorry. So in red, you have the models, and in black, that are the observation. Each model is linked to a different type of Keplerian rotating disk. Then you have the VLT Pioneer observation by Kleska in 2019, where this is in infrared in H-band, and here you can see that we can actually see. Of course, it's interferometry, so there's a reconstruction of the image, but you can actually see the circumbinary disk. And unfortunately, you might not be able to see it, but on those 2, you can actually see the 2 components. So the big dots that you're seeing there, it's one, but there's also a fainter one, which is the companion. So we can see the binary system and we can see the disk. So we're starting to resolve all the ingredients to have the non-spherical objects. So here, for example, it's the post-AGB star RV tau. So this is a reconstruction. This is, sorry, not a reconstruction. This is an image of a system where you can see the binary stars. You can see the circumbinary disk. So this is based on a work by Vega in 2021, where they detected, for example, not only the binary system, but also the circumbinary disk. And in that work, this was the first time that we detected X-ray in the post-AGB stars. Remember, those things are 7,000 K. So where does this X-ray come from? So this is an open question. But also, and we will see a bit later, this is one of the only post-AGB stars to have magnetic fields. And this is also one of the post-AGB stars with jets. So it's got all the ingredients normally to be a non-spherical planetary nebulae. So all those are the observations that you can see, for example, in the SMA, where you can see an image of the circumbinary disk. Okay, we were talking about jets and outflow. So they've been looking for outflows for jets, being an important ingredient in the shaping mechanisms. So Gallardo-Cava in 21 find jets in CO, and 12 CO and 13 CO in a post-AGB 89 Hercules, actually. And you can see the outflow masses, actually didn't translate well here, 10 to the minus 2 to 10 to the minus 5 solar masses, and the expansion velocity below 10 kilometers per second. So I just wanted to point out something. When I'm talking about outflow, I'm talking about things with velocities below 100 kilometers per second. Jets are above 100 kilometers per second. Then you have a more recent work by Bolen et al. In 21, where they detected jets using optical, using high resolution spectroscopy with the Mercator. The resolution was 85,000. And here you can see their observations and for different models of jets, stellar jets, X-wings, and X-wing. The difference is basically where the magnetic fields, which is powering those jets, is coming from. In the stellar jet, the magnetic field is coming from the stars, and in the X-wing and disk-wing, it's coming from the accretion disk. So something interesting come up here is that we have our jets, but they are all, whatever the models, they are all linked to magnetic fields. Another ingredient. So let's see what about magnetic fields in those post-AGB stars. So we've been looking for this for those fields in different ways. For example, here, this is a work that we've been doing for the Calabash Nebulae. So basically, we are tracing the field using dust polarization. You can do that for dust, but you can also do that for molecules. I'm not talking about masers. I'm talking about non-massing molecules, for example, like CO. So this is a work from Wang et al. In 2020, but there's a new work from Vleming and Tafoya in 2023 for another post-AGB stars. So using the polarization of dust, using the polarization of molecules, you can trace the magnetic field in those objects. But what we are also interested in the intensity of the magnetic fields. To do that, we can go on the stellar surface of the photospheres of those objects. So here, this is a work that we've been doing in 2015 with Humonocerotis, sorry. So this is the one that I show you with all the ingredients. So what you can see here is this is the Stokes V, and you can see the nice Zeeman splitting in these objects. So this is one of the first objects with a detected magnetic field and the fields in the order of 10 Gauss. There was another recent work by Georgiev et al. In 23, looking for the variation of the magnetic fields in post-AGB stars. So this is the other post-AGB in which we found such field. This is RSQT, and indeed the field is varied. So just look at the square, which are the direct detections. So the field that was measured was about 1 Gauss, but the variation is going from is going up to 2 Gauss, basically. So it's very short variation. Post-AGB stars are also the host, if I can say, of synchrotron emission. Actually, we only found that in one object. So this is an article by Perez Sanchez in 2013 when they detect negative spectral index for IRAS 15445. And what they claim is that the jet that they are seeing is powered by magnetic launching. And finally, the masers, as I was saying at the beginning, this is a work by Leal Ferreira in 2013, when they detected masers in another post-AGB. Actually, they detected masers in plenty of post-AGB stars. And in that example, the maser is in the order of 45 milligauss. And if you trace that back to the stellar surface, it was giving a magnetic field of a couple of Gauss on the stellar surface, which is in accordance with what we have found directly. But the problem with maser is that masers are locals. Maser will not give you a picture of the whole magnetic field in your target. So that's the only issue. Okay, let's jump from shaping to nucleosynthesis. So we've seen that abundances are very important in those objects. So post-AGB stars are short-lived up to like 1,000 years. So it's really something, cosmically speaking, is extremely quick. And what you can do with those post-AGB stars is that they are tracers of the nucleosynthesis that occur in the AGB. So this is a graph by Kamat and Van Winkel in 2022. So on the top line, this is the stellar spectra of a post-AGB without S-process enrichment. And the two below is where you have S-process enrichment. So those S-process elements will enrich actually the post-AGBs, and they will also enrich the galaxy where they are. So something that they also were looking for is that the bimodality that they found. So here in blue, you have all the objects which are non-S-process enriched, and in red, the S-process enriched objects. And they were always seeing that bimodality, and they were wondering, where does it come from? Is it linked to the fact that those objects have different luminosities? And if they have different luminosity, that means that they have different initial masses. So the problem is that all those objects have the same similar effective temperature, they have similar metallicity. So when they used Gaia, again, Gaia was a very important player in the game. So when they used Gaia to calculate accurate distances, well, they saw that actually that has nothing to do, that bimodality has nothing to do with the luminosity. So maybe in the post-AGB family, there's a rich chemical diversity. So that diversity can come from the fact that we have rotation, that we have extra mixing. Well, we don't know exactly yet. And I will finish with planetary nebulae with planets. So those are the most recent results that we have. So CLUSCA in 2022, what they did was they studied disk around post-AGBs. And if they studied this, that means that those post-AGBs are binaries. What they looked was the transition disk. And they found a link between the depletion at the stellar surface and the disk. Basically, what they could see is that the disk around depleted sources were transition disks, and the disks which are not strongly depleted targets are full disk. So basically what they postulate is the existence of a mechanisms that separate the dust and the gas in the circumbinary disk. And this is actually what they state word for word in their article, that a natural explanation would be the presence of a third component in the system that carves the disk hole in dust by acting as a filter, trapping the dust in the outer disk, but still letting the depleted gas to be accreted onto the central stars. And that third component that they are talking about, it's a planet. There's no detection here. There's no direct detection. They just infer that they could be the presence of a planet. The other work, which is even more recent, was Martin in 2023, where they studied the ACR, and what they found is that the binary orbit of ACR was at 90 degrees from its circumbinary disk. So it's a polar distribution, a polar alignment. And what they postulate is that there was the inner edge of the dust disk. If you're looking at the darker place, which is actually what they observe, well, the inner disk is much farther out than the tidal truncation radius. That means that, again, something is carving this space here, and that something could be a planet. So basically, in both cases, there's no direct detection of a planet. It's just an assumption based on the orbital elements, on the study of the disk, on the study of the geometry of the disk, basically. Okay, so now we're leaving the post-AGB phase and we're looking for the planetary nebulae. What's happening in the planetary nebulae? You have a fast wind, like 1,000 kilometers per second, that basically is stripping your central star from its material. The central star now is going on the left on your HR diagram, meaning that the temperature are increasing. When the temperature is above 30,000 K, more or less, you start to ionize everything. So when all your circumstellar envelope is ionized, you have a planetary nebulae. So you have an expanding shelf, which with time will dilute in the interstellar medium. So if you want a good review on the evolution of planetary nebulae, I will suggest the one by Quitter and Henry in 2022. So casually, a couple of months ago, there was the IAU 385, the IAU on planetary nebulae. So during that meeting, we stressed a bit more what are the characteristics of planetary nebulae and what planetary nebulae matters a lot. Planetary nebulae trace stellar evolution. Basically, they are the connection between the giant and the white dwarf. Planetary nebulae, you're able to compute mass losses, the stellar winds, binary interaction, etc. They are the tracer of lots of hydrodynamics events. We're going to see the shaping of the stellar wind. We're going to see the jets. I'm going to talk about that in a minute. They are astrochemical laboratories. Here you can study molecules. You can study pH. You can study fluorines, dust formation, and dust destruction, for example. The abundance are really important in planetary nebulae, and I will show how we developed really sophisticated tools to calculate those abundances. Here you have all the physics that you can dream of: atomic physics, photodissociation, shocks, the study of forbidden lines and recombination, etc. And finally, planetary nebulae are an extraordinary tool when you want to study other galaxies, whether it's about distances, whether it's about abundance gradients. Even some say planetary nebulae can help you with dark matter and cosmology. Don't ask me about that because I don't know well, because it's a very recent, really recent subject. And actually during that conference, I think it was the first time that someone was presenting something between the connection between planetary nebulae and cosmology. So one of the participants of the meeting said that planetary nebulae can solve any problem in astrophysics. So we are the good one. Okay, same. What has been done during the last 6 years? So basically, people have been working on having more planetary nebulae, establishing a catalog of planetary nebulae, studying the abundances, the kinematics, the binary, etc. And also, yeah, so I said it, sorry. Okay, so what are the open questions right now? So we have those open questions are somehow sometimes similar to the post-AGBs. It's just that we move one evolutionary steps. So first, the progenitor evolution. What are the processes leading to a planetary nebulae? We would think that, well, we have been studying planetary nebulae since, I don't know, really well. I mean, since like the 70s. So you would know that by then we should know everything, but not really. The problem, I guess it's a problem for everybody. The more we find, the more we have to find. I mean, the more we think we're getting close to the solution, the more other problems arise. So we have to solve each time other problems. That doesn't mean that we're not making progress, but we have still lots of things to know about the evolution of the progenitor. For example, the shaping mechanism, the same. Why do we have a spherical planetary nebulae? The chemical composition, what is the exact composition of planetary nebulae? And we're going to see that in a minute. The central star evolution, or the central star evolved. We're going to see that there's different paths in the evolution of central star. There's not just, I'm going from, I don't know, this my 30,000 K central star to the white dwarf. No, it would have been too easy. So nature decided that we're going to have a lot of different paths to go to there. So we need to study that. The 3D nebular dynamics, that's really important because this is something new. We see better in 3D. We have a better comprehension of the expansion, for example, the kinematics of planetary nebulae in 3D. Jets and outflow, the same as we've seen for post-AGB stars. How jets and outflow are important and carve your planetary nebulae. And also, what are the mechanisms that produce those jets? The role of binarity, same. How binarity acts in the shaping and also in the chemistry of your object, in determining the chemistry of the post-AGB stars. And again, planet. How do they relate to planetary nebulae? So again, we're going to start about the sample. Right now, we have 4,623 known planetary nebulae. The true one, because we divide them in true, likely, and possible. The true one are only 3,264, sorry. And they're all listed in the H catalog. Basically, if you want to know about planetary nebulae, you have to go to that catalog. So here, this is an extract of what is giving you in that H catalog. So, okay, we have so many planetary nebulae, we should be happy, but of course we are not. Why? Because according to different evolutionary models, we should see more than 20,000. And some people said we should be at least 60,000 planetary nebulae. So we are a bit short in numbers. So we've been doing lots of surveys recently. We have been the MASH survey from Parker, Mizalski. This is in the Southern Hemisphere. We have been the IFAS survey in the Northern Hemisphere by myself and Andreas Ritters. There's the VIFAS survey, which is the same as the IFAS survey, but in the South. So there, to detect those objects, there's different technique, visual detection, the old-fashioned one, photometry. Vironen and Tan applied such technique for IFAS objects. And of course, now that we are in the era of big data with machine learning by Sun et al. In 2023. So what are the characteristics of those new PN that we are seeing? Of course, those new PN are fainter. That's why we didn't see them before. So they are faint, they are large, they are more evolved, but also surprisingly, we have some really compact and bright. So how did we miss those ones? Well, basically, they were in plain sight. So if you have, let's say, a cluster of stars, and you have your very compact planetary nebulae, so at naked eyes, that's another star. So people were not looking for those objects. They were not able before to separate those objects than the stars around. But now we can do that. And something very important that I really want to stress is the significant contribution for amateur astronomers. So we've been working with a group of amateur astronomers. The DSH, the Deep Sky Hunters, they have a site web, which is planetarynebulae.net, where they have a compilation of objects that they are detecting. And for example, this one is Kronberger 61. It's a planetary nebulae that has been found by Matthias Kronberger, he's an amateur astronomer. And we've been plenty of professional amateur collaboration leading to scientific articles. There's one by Le Dieu et al. In 22, in Jacobi 21. In a minute, I will show you how they impact greatly our field. And of course, for all those new objects, we have plenty of follow-up, spectroscopy follow-up, imaging follow-up. So we are building our sample of planetary nebulae. It's slow, but we're getting there. So the important thing in planetary nebulae is the shaping mechanisms. Again, the same question as post-AGBs. How do we have so many non-spherical planetary nebulae? Just to give you a number, if you have 100 planetary nebulae, 80 will not be round, will not be spherical. Just to keep that in mind. So we were wondering, why do we have such numbers? Where does this shaping, well, where those bipolar, those multipolar, those point symmetric shapes were coming from? So we had plenty of discussions in the field. We are a very nice community, so there were no fights, or well, more or less, to know what was the mechanisms that was shaping those planetary nebulae, and we finally arrived to a consensus. It's binaries. So basically, the main mechanisms is responsible for that is the presence of closed binary system. So if you have a closed binary system that has been through a common envelope, so that means that you have two stars, one which is filling its Schwarzschild lobe. So two stars in the end are inside that circumstellar disk. Material is accreted around the secondary. You have the ejection of a jet, and you have your bipolar or multipolar planetary nebulae. So everybody was happy because it was fitting with all the fitting with all the models. And now we were discovering more and more closed binaries objects. So there's the article, I can reference the article by David Jones. David Jones shows in both in 2017, 2018, 2020. Actually, Dave is keeping a database where you can see all the binaries, not only the closed binaries, but also all the binaries detected in planetary nebulae. So, and something again, Gaia helped a lot, so we can have the distance of those objects. So here, for example, you have the Nicholas nebulae, which is a binary, closed binary planetary nebulae. And you have this, so the central star, which is actually, there's two components, and you have those jets. And that ring of nitrogen 2 knots. So if you think that, okay, we made it, we finally solved one problem in the planetary nebulae field. Of course not. So what we've recently, actually, there have been some voices raising concerns. Basically, Mo and Di Stefano in 2017, and more recently, Miller-Bertolami in 2022, say that, wait a minute, not all PN are in a closed binary systems. Actually, most intermediate mass in binary system will, those stars will never interact. And remember, 80% of planetary nebulae are non-spherical. But here we know that most of intermediate stars will, in a binary system, do not interact. Okay, so that's another problem. The other one is that, well, lots of people using MHD models said, okay, maybe binary can have, even we give you the closed binary. Closed binary system can do the job in shaping those objects, but you can do that without magnetic fields. You need magnetic fields to launch those objects. So you must have these ingredients. So basically right now for lots of people, and actually it's not just in the planetary nebulae, in other community as well, where you have jet launching, they stated that magnetic fields are crucial. It's not indispensable to launch the jets. So it's as is it's true in an Herbig-Aero, is it true in an AGN? Well, it's true as well in a planetary nebulae. So there has been plenty of models by Garcia Segura in 21, 22, Blackman and Lebedev in 22, Balik in 20s, Allman in 2016, trying to model those objects. And here you have some result by Garcia Segura on his article on 2021. And here you have the observed object is W43A and the model. The Calabash Nebulae, the one where we find these X, we observe, we trace that magnetic field in the X shape, and this is the model. Both models includes magnetic fields. If they do not include magnetic field, you cannot reproduce this. Those two objects are not planetary nebulae. Those two objects are post-AGBs. Why I show them there? Well, because those their studies have shown us that magnetic fields, well, the shaping, most of the shaping, if not the majority of it, occurs during the post-AGB. When you shape your object, you do not shape it during the planetary nebulae phase. You shape it during the post-AGBs. In the planetary nebulae phase, the magnetic fields is no longer dynamically important. So this is something that the MHD modeling is telling us. So we were talking about jet launching. So there's been plenty of modeling and observation about jets. So Zhu et al. In 2020, what he did, so here you can see, so those are different models, but here what he did, he didn't include magnetic fields, he just included the interaction between fast winds. If you have the interaction between fast winds and a previous dense equatorial plane, well, you can have that kind of object. So he said that, okay, you not necessarily need all the time magnetic fields to launch your jets. Of course, you're not gonna have the exactly the detail of some of the post-AGBs. You cannot reproduce the detail of what that we see in some planetary nebulae stars, and post-AGBs as well. But for the most simple bipolars, that can work. Guerrero and al. In 2020, they observed the distribution of 58 planetary nebulae, and they see that 30% of them showed collimated outflows. Jackie is here, and she gave a talk yesterday that showed us the jets as well in those planetary nebulae, observed with an IFU, Megara, at the GTC, and she's got plenty of articles on that on 2020, 21, and 22. And here you have the PV diagram, then you can see these jets up to, if here it's your 0, you cannot go at minus nearly 300 here. And here you have your, you can have with the IFU, you can have your tomography of the jets. So we do find jets in planetary nebulae. Are they related to the same jets that we are seeing in post-AGBs? Are there new jets? How long those jets are lasting? So those are new questions that we are having. So as I said at the beginning, the more we discover, the more we have questions. Those we couldn't see that before because we didn't have those type of instruments, of high resolution instruments. Abundances, another important thing. The planetary nebulae abundance, they are really tricky. So there's a long-standing problem in the planetary nebulae is the ADF, abundance differentiation factor. Basically, when you calculate your abundances using a collisional excitation line here, or the optical recombination lines, but we do not have the same results. So we've been doing plenty of work to have the best photoionization codes, PINEB, PiCloudy, the 3MDB, but we really need high spectral resolution to be able to disentangle the to have those maps of the distribution of those different ions based on the process that create them. So using Muse, so all those are the data from Muse. Now you can see, for example, this is the O++ over O+ in CEL and recombination line, and you can see that there's a difference in distribution. So this is something new as well that we didn't have an idea before, but now with the high resolution, we can do maps with the high resolution, and if we can do maps and we can have a better understandings. So there's we're still struggling, as they said here, to detangle shocks and photoionization. There's two mechanisms occurring in planetary nebulae. There's the case of low ionization structure. So Denise Gonçalves in Brazil and our group are working hard on this. The abundances based on molecular line are also something very important and not a problem to add in the calculation of abundance in planetary nebulae. So Richard and in 22, well, basically what they said is that although they study a planetary nebulae in GC 6153, and their conclusion is that although there are complications, multiple plasma component, temperature fluctuation, and contribution of multiple physical processes to a given emission lines all are part of the reality in NGC 6153. So you have to take into account all those things to be able to have the best abundances in your planetary nebulae. And more. So I do not have the time to go through all of them, but there's with planetary nebulae, we are able to have distances at the statistical or with Gaia, the planetary luminosity functions, to characterize extragalactic planetary nebulae, but I will actually stop on that, the new evolutionary models. So in 2016, Marcelo Miller-Bertolani published new evolutionary models. And what those models are telling us is that the time scales are much shorter than what we thought before. That means that the time to go through the post-AGB to planetary nebulae is really much shorter than all the different models that we were relying on in the past. And what are the implications? Well, all those models are linked to the calculation of initial and final mass. So, so that was not a well, that's a good news in terms of astronomy, but for us, that's not a good news because that means that we have to recalculate everything. Okay, just quickly, just to show you that this is NGC 3132, which is one of the first, the first planetary nebulae which has been observed by the James Webb, one of the first image of the GWST. And this is a contribution of basically at least half of the PN community contributed in their own field in analyzing these objects. Okay, so we had open question. Now, after all those studies, we have new open questions. So I will go through some of them quickly, as I'm running a bit out of time. So what planetary nebulae can tell us about the evolution of light process element, the need for us to study molecular line, and trying to understand the ADF, the abundance discrepancy factors. That means the difference between the abundance calculated between collision excitation, the collision excitation lines and the recombination lines, the jet tracing, as I was telling you, the fact that we need to be able to trace the shocks and to discriminate them from the photoionization. New instrument like mining eROSITA, and mining into the eROSITA data might give us really very good sight, of the X-ray in those planetary nebulae. The binary problem, or the binary affect the post-AGB and the post-AGB, the common envelope jet interaction, etc. Okay, so I'm gonna go quickly on because really I'm out of time. So just to say that white dwarf in planetary nebulae, we have been working on this, but it's really another group of people working on that. So there's a lot of variety of CSPN. There's been large amount of white dwarf in Gaia with and the SDSS, and the detection of planets around white dwarf. So we have really a detection of, candidate planets in that case. This, and I will conclude on that, it's the progenitor of a SN1A object. So double degenerate and single degenerate white dwarf can give you a SN supernova remnant of type 1A. This is one of a kind, is white dwarf G005311. Why it's important? For two things. It's a merger between, first it's a merger between, it's a double degenerated case, ONE and CO, or 2CO, they don't know yet. And the nebulae that you can see here is a type 1AX supernova, the only one known in the galaxy. And the most important thing here is that that was discovered by an amateur astronomer. Okay, there's a big family of objects, born again, nova, symbiotic, CVs. Dennis will talk about symbiotics in a different occasion. All involving binaries. So here are a bit of things that we have been studying. The born again objects, you can ask me for that later on. The symbiotics, the fact that the symbiotics, we have now something that we can do is to fit models that we use for AGN for those symbiotics. And the important thing is that they all is the stellar feedback, all the material, the process material that they're giving up to the interstellar medium. In Mexico, we've been doing plenty of research on that. We are a very active group. With a lot of activities. I'm going to stop that just to say that we have, plenty of students, actually. There's a bright future for the study of evolved stars with plenty of facilities in Mexico or in Latin America. So we have to do that. If you're interested, again, let me know. And I'm really, really running out of time. So thank you and sorry.
Okay. Questions for our colleagues? Yeah. There.
Hola, Laurence. Muy bonita plática. I have a question about the planets in AGB stars that you were mentioning. So these are planets that are formed in situ in the disk of the AGB star, or are they pre-existing planets?
They don't know, actually. There's no, all these, as you've seen, those are really, really recent results. And they just, in one case, in the post-AGB case, they infer that there's the existence of a planet. Where it is from, they don't know. They do not have any idea about that. Maybe it's in the, it can be in the, in the shell, in the circumstellar shell of this, but we don't really know where it's come from. That's why it's really interesting to see those, to have more of them. But we really have a very small sample, and they do not have an idea, actually, a clear idea yet.
Thank you.
More questions? See. Where? Okay, over there.
It's maybe a very basic question that I should know, but how do we know when is the transition from the post-AGB to the planetary nebula? When we say it moved from one to the other, where is the division?
One word: ionization, photoionization. When you start when all your shells ionize, and which is linked to the temperature of your central star, then you have that separation. That means that, for example, the canonical temperature is like 20,000 Kelvin. At 20,000 Kelvin, now most of your shells, the 90% of your shells, is ionized. So here you are a planetary nebula. Below that, you are a post-AGBs.
Okay,
but that's not a basic question, because actually that transition, because the times are so short, so it's quite difficult. For us, it's very important to have, we have few examples of objects that are exactly at the transition. So this is also something that is studied, actually.
Okay, thank you.
We have time for more questions? Yeah.
Hi, Laurence. Thank you. Another basic question. So can these putative planets play a role in the collimation, like a hot Jupiter, or are they too small?
Yes, so something that I didn't say because I didn't have the time. Thank you for the question. So planet, we first started to be interested in planet in the field of planetary nebulae because of the shaping. Because we had models, for example, those from Eva Villaver in Madrid. She was doing plenty of models to see if the shaping could be due to a planet. So let's say that we have our sun and Jupiter's. So you let evolve all this system, the sun's going through all the planetary nebulae phase, etc. So maybe instead of having a stellar companion, the planet, the Jupiter mass planet, could do the job, actually. So that was something, and the models say that it worked. So that's why the reason why we were interested in planet, for the shaping first. And now we started to see. We started to have ideas that planet, not ideas, but we really have some proof. I don't want to say some proof because we do not know exactly if they are there, but we're starting to observationally have insights into the presence of those planets. Paradoxically, not in the planetary nebulae phase, before and after. In between, we do not see them, but that the shaping was the main reasons.
Thank you.
We have time for one more question over there.
So this circumbinary material, how long should it last, and should we see many of them in compact binaries or not?
How long does it last? Well, I would say it lasts as long as the planetary nebulae will live. Like, it's really something that will disappear after, maybe for the most massive objects, maybe 30,000 years. a bit more, maybe really it's depending of the mass, of the initial mass of the objects. But when you are when you start entering in the white dwarf phase, well, all this has already been diluted in the circumstellar environment. In some of the oldest planetary nebulae, which generally are the most massive, the one that you can still see the bipolar shapes, and those things are, I don't know, more than 30,000 years. Sometimes you can still see a remnant of these disks. So that means that those things were really massive. So they were on the upper limit of the mass for planetary nebulae. But once you go through your white dwarf phase, well, those things will dilute and you won't be able to see them. Well, actually, this is what we think, because just something that's maybe observing more of those white dwarfs, for example, in radio. So maybe there would be some reminiscent of this, but generally we don't see that.
Muy bien. Bueno, agradecemos una vez más a nuestra colega. Creo que, ¿no? Ya. Ok, entonces ahora vamos a dar paso a nuestro siguiente orador, que es Bruno Dias, de la Universidad Andrés Bello en Chile. Gracias.
Buenos días a todos, todas. Muchas gracias al SOC por invitarme, al LOC por toda la organización acá. Un gusto estar acá compartiendo con ustedes, ya un par de LARIM que he estado. Y agradecer, o sea, mi universidad, también el Fondesit, que me ayuda a estar acá. Queria dizer que eu sou brasileiro, mas trabalho no Chile, né? Então, eu acho que cabe muito dizer isso aqui dentro do contexto da LARIM, que é para colaborações e internacionalização. Então, gostaria de destacar isso, né? Y ahora que estoy en Chile, bueno, ahí me recibieron muchísimo bien en Chile, y con las puertas abiertas y me esperando en la puerta, en la entrada, y sonó incluso un poco raro, que dicen, no, o sea, no soy tanto para eso, o sea, como llegué acá en Chile, pero bueno, ahí descubrí que al final la razón, ¿no? Bueno, well, so today we'll talk about the VISCACHA survey. So the VISCACHA survey is a group of people, right? So I always like to show people, because science is about the nature, it's about the universe, but the galaxy will not stop interacting to each other if you don't understand that. So it's how people try to use our intelligence to understand what's happening in the universe, right? So, and today I will talk about the VISCACHA survey, but I'm a single person here on behalf of all the entire team. And also because of LARIM, I like to highlight some things that the VISCACHA survey is a Latin American collaboration. So that's producing very high level science, worldwide collaboration and impact. And I just like pointing here at least the first authors of the papers, where they are located here in South America, for example. There are other countries, other regions here of people in the team that are collaborating, and a couple of PhD theses as well happening. So that's about people. So let's go for science. Who of you has ever seen the Magellanic Clouds by naked eye in a dark sky? Amazing, right? So they are amazing. That's because they're really nearby the most massive dwarf galaxies in the Milky Way. So this is one of the reasons, of the main reasons, for bringing telescopes to the southern hemisphere. So this is for radio, for optical, infrared, and everything. And these are very interesting cases. And why? So one of the reasons that in the 70s, there was a map of gas in the whole sky that they discovered there was a trail of gas trailing behind the orbits of these galaxies of 200 degrees wide. It's huge, huge on the sky. So it calls the attention. And people wonder why. So we saw the talk by Yara talking about ram pressure. So you know about that. But recently, 20 or 30 years ago, or 20 years after the discovery of this trailing part, they discover also a leading part crossing the Milky Way disk. So that's harder to detect because you have the gas in the line of sight from the Milky Way, but it was confirmed. So that means that there is some tidal forces happening, not only the ram pressure, but tidal forces. So that's gravity. So not only the gas, but also the stars are moving. So stellar populations can tell us a lot. And to explain that, there's been a canonical scenario that we call bound, where the large Magellanic Clouds, the LMC, and the small Magellanic Cloud, the SMC, they were orbiting the Milky Way for a long time, and they recently became a pair. I don't know, 2-3 billion years ago, they synchronized their orbits around the Milky Way, but they have been always around the Milky Way. And that was enough to produce this trailing part of the Magellanic String and also the leading arm crossing the Milky Way disk. But recently, in 2007, there was a change of paradigm. There was a paper by Gurtina Besla with a title with a question, but with new evidence, observational evidence, new models, saying that, or proving with simulations that it is possible to produce the Magellanic Stream, which is the trailing part, and the leading arm, which is crossing the Milky Way disk, by a different paradigm, and which is that the two galaxies, the LMC and SMC, they have always been a pair, but away from the Milky Way. And they just arrived to the vicinity of the Milky Way. And this also can produce these beautiful structures on the sky. So they are two completely different paradigms, and they both can produce the large-scale structure. So how do you decide between them? So we need more independent evidence. We need to go for the detailed, small-scale structures, and that's why I'm here. I think a last note about people. No, not last, but we saw the statistics that we have 53% of students in the audience and 40% of women, if I remember correctly, from Gonzalo. And so I would like to highlight this fact here that Gurtina Besla in 2007 made this change of paradigm. And she was, I don't know, first, second year PhD student, a woman. So just to have this note here for you to feel that you can do incredible things. Here's a list of evidence, observational evidence that I try to list. When I have more time, I go one by one. You can ask me later if you are interested in some of those. I'll just highlight here the difference between the bound, the classical scenario, and the first infall, which is the new one. So just going to the third line here, this local wake and the northern overdensity. So this is something that the bound scenario cannot explain, and the first infall, yes, because it's by definition. So what it is? Essentially, if we have this canonical scenario where the two galaxies are orbiting around the Milky Way, the gravitational influence in the stars, in the halo of the Milky Way, will kind of dilute, right? So they will impact and will be diluted. But if they're in the first infall, they are very massive. The LMC is 10% of the mass of the Milky Way. So the impact of it will cause some clumpiness of stars around the Milky Way halo. And that's exactly what they found, and there was a Nature paper. So this is only one of the evidence that's supporting this. So people are collecting more and more evidence towards this. So it's becoming the new paradigm and the new reality, let's say, our understanding. And here we are talking about the Magellanic Clouds, but okay, so there are two galaxies, what they tell about galaxy interactions, evolution, and so on. So yeah, so there are many galaxy interactions that, again, the Yara showed a lot of examples of interactions there, and some of them are listed as possible Magellanic Clouds analogs. So pairs of galaxies there. So we have the advantage to have in our neighborhood, to resolve stars, to have 3D shape, and all the detailed information we want in our neighborhood, so in our garden then. So we can use them as probes to try to constrain some extragalactic studies. Well, but my title said that I would talk about star clusters, so what about them, right? So Laurence mentioned that planetary nebula can solve all the problems in astrophysics, right? So I think that star clusters are as powerful as the planetary nebula. So with star clusters, we can have two views of star clusters. Let's say we can look inside, right? So that's astronomy 101, right? So you can study stellar evolution, star cluster dynamics, and so on. So looking very smaller scale, or you can use a population of star clusters in a galaxy to constrain the galaxy itself, right? So that's why we chose the star clusters. So with the VISCACHA survey, we can do all this type of projects, looking inside and as a big sample. Of course, as a big sample requires a lot of observations accumulated to get the statistical significance we need. But here, just to show some techniques for those that are not familiarized. So this is the density of stars as a function of the radius, the same for the luminosity. And this is the color magnitude diagram. And this is the luminosity function converted to mass function. So these are the type of techniques that we use, and then we derive parameters from that. Okay, but there are many surveys, photometric surveys, all sky surveys, Magellanic Clouds dedicated surveys. So why do we need another one dedicated to star clusters? The problem is that star clusters are very crowded regions. So the typical surveys, they are seeing limited. So you cannot resolve the stars in the cores of this cluster. So I just show an example here of two images of this. So this is a VISCACHA image on the left in color. If I can get the, I cannot find it. Well, here. So this is the VISCACHA image. And here I compare the VISCACHA with this mesh, just to give an example of two telescopes in Chile, very nearby, same sky, 4-meter telescopes. But there is a huge difference here, which is adaptive optics, right? So that's the niche that we're exploring here with VISCACHA, is to provide complementary survey dedicated to star clusters where the seeing limited surveys cannot reach, right? So here's an explicit example of the color magnitude diagrams. If I split the same image in rings, so the external part are sparse filled stars. So both surveys, both photometry are very similar. So they're okay. So there is no advantage of using VISCACHA here. So we are focusing only on the star cluster. If you go to the core, you can see that we can reach down to the main sequence with good photometric errors and the entire thing. And here you start losing low mass stars really quickly. So this is what we're exploring here. To put this in a plot, we could go to space, but Gaia is shallow photometry, so it doesn't reach the old stellar populations. And HST is usually pinpointing the massive clusters in the bar or the very crowded regions in the center of the galaxies. So we cover the outskirts, and then we complement with Gaia, with Hubble, and we are done with the sample. So here's the sampling in the SMC. So I'll be focusing a bit on the SMC. I cannot talk about everything. You can ask me if you're curious about other projects. So I just chose a few projects there. So in the SMC, so that was in my PhD thesis, I started studying this. So that was before VISCACHA, kind of the seeds to build up VISCACHA survey. So we focused in the outskirts, and I realized that there was some regions here that I could split azimutally, and they were related to some interactions of the Magellanic Clouds, among them with the Milky Way or something. So the data we use here is a combination. So the VISCACHA, we have to do statistical decontamination, right? So we have some software to do that with Bayesian statistics and some smart moves here comparing with the related field. And we can finally do also isochron fitting, synthetic SMD fitting, and we get, for example, age, metallist, and distance from this. And with a follow-up spectroscopic survey for a few selected clusters, we can get radial velocities and also corroborate the photometric metallicity with the calcium triplet lines. And from Gaia, as I mentioned, it's a shallow photometer, but also for the proper motions, it's not possible to use a proper motion selection. So as we do for Milky Way disk, for open clusters, for example, that's easy, straightforward. You can just like pinpoint even distances, right? But at 50, 60 kiloparsecs away, we cannot do that. So what we do is to select the star first from spectroscopy, from other techniques, and then you go to Gaia and ask Gaia what are the proper motions there and get the average. So that we cannot get individual stars proper motions, but we can certainly get the mean proper motions for a single cluster. So that's enough for this type of study for populations of clusters. So for example, with the SMC again, come back to this plot, what we've been collecting here, actually for the first time, we are doing the full phase space vector of these regions of the SMC, including so the 3D position, the 3D velocities, combining all the data because we have the star cluster. So again, with the Magellanic Clouds, they're in the neighborhood, so you can have the 3D shape with full of informations with ages, metallicities, and even chemical abundances if we go for high resolution and so on. So the SMC, for example, is 4 kiloparsecs across the sky and 20 kiloparsecs along the line of sight. So the distance really, really matter. And the initial conditions for the SMC are really, really a sensitive initial conditions for all the simulations. So it's really important to derive that to understand the broad context. Here, just to put some more brutal data, that was just a cartoon before. So the crosses and circles here are the subsamples of the VISCACHA survey as we are building the papers. So this is this part here is what we see on sky. So this is the northern bridge, the southern bridge, and western halo. And here's adding the line of sight distances. And here's the Cartesian conversion of that. But the point is that the east part that's pointing to the LMC is the bridge. It has 3 branches. So usually you think about one bridge, but it has the 3 branches. They're closer to us, so they're going away from the sky because the LMC is closer to us. So it's pointing to the LMC, as you can see here. And it's also moving towards the LMC. And the opposite part is kind of a shell that's moving away. So this is also consistent with some simulations, dedicated simulations. Right, so this is part of the structure and kinematics. So what can you do with chemistry? So we get ages and metallicities, right? So we can simply build the age and metallicity relation. So also Celeste Parisi from Argentina has been collecting for ages calcium triplet metallicity. So spectroscopic metallicities, homogeneous, accurate, and she found that there is an intrinsic dispersion in metallicity for intermediate age clusters. And then all these lines here are different chemical evolution models trying to reproduce this mass, and they cannot. There is no single model that can reproduce everything. So there's a big dispersion that's not related to observational errors. So how do we solve that? How do we understand this, this thing? This is part of what I proposed when I was a PhD student, to split the regions, because each region is telling us a different story. So what happens when you do that? Some magic happens. So there was a PhD student of my student in Chile, Sarun Sassi. There was a published paper already this year, focused on the Western halo. So what happens if you get the age metallist relation only of this region? The dispersion goes away, and magically some metallicity dip appears. 0.5 dex something. We run some models, and for this to happen, it must have an infall of a pristine metal poor gas that could be related to a major merger, for example. So for this to happen, we need a major merger. And this is not out of very crazy idea, because with the collecting evidence here in the first infall new paradigm scenario, some new evidence are telling us that the LMC is not infalling to the Milky Way, bringing only the SMC. But the LMC has its own system of smaller dwarf galaxies. So with Gaia, Hubble, many proper motions, kinematics, or orbital. So there are many evidence pointing towards that. So it's not super crazy idea to think that maybe the SMC is the composition of 2 galaxies in the past. Who knows? So this is a chemical evidence for that. Only using photometry from star clusters, very accurate in a dedicated survey. So that's huge conclusions only for pinpointing this as a population. So if you go for simulations, so the simulations, there's a long road ahead, but there are some evidence there, of course, for a close interaction between the SMC and LMC about that time. And also if you go for the histogram of ages of star clusters from the VISCACHA catalog, you see a peak of clusters around that time as well. So I think that's converging. There was another PhD thesis working on different regions in the Magellanic Bridge, so what we call the Wingham Bridge, so that's the young branch, so the central, the main branch that's coincident with the gas bridge, okay? And he found, again, so this is the big dispersion that it's homogeneous and so on, and the yellow points are those dedicated to the Wingham Bridge. So you can see again that the dispersion decreases a lot. And if we zoom in here, there is also a metallicity dip around 1 or 1.5 billion years ago and another 200 million years ago. And they are completely different from the chemical evolution of the West Halo. And what happened at these time scales? The Magellanic String was formed about that time, and the Magellanic Bridge was formed more recently. So some of the external galaxy-galaxy interactions are imprinting some signatures in the star cluster population. So that's very powerful. So I just want to give one example here of the internal structure of star clusters, just to show that what we are doing with individual star clusters. So here's a statistics from the literature and putting together now, accumulating now new data from VISCACHA, trying to be homogeneous and precise and so on, of mass versus ages. So if you think about cluster dissolution, so cluster dissolution is an internal process. So star-to-star interaction, if you have a binary, a black hole, whatever, is moving stars away, right? So usually we start have internal evolution, but we can discuss that later if you want more details. But the clusters start to lose stars, usually from the outskirts and usually lower mass stars, preferentially. And the potential of the cluster, if it's too shallow, which means lower total mass, it will be easier for the stars to move away. So if you're looking for star clusters that took their time to evolve and they're lower mass, so around this region, we think that it would be more likely to find clusters that are currently under dissolution. In our first paper, that was 2019, we find one cluster that was 5-6 billion years old and very low mass. And here's the mass function, right? So here's the high mass part, and this is the low mass part. And it's missing a lot after correcting for completeness. It's missing a lot of low mass stars. So we believe that this cluster, we caught them under dissolution right now. So this is one of the examples that we are doing this, trying to connect the internal structure with some external forces. And why external forces? Because the internal structure is responsible, the interactions between stars is responsible for the dissolution, but it can be boosted by external interactions. So what happens here? So a little bit of comparison between what we call the Jacobi radius and the tidal radius. So the Jacobi radius would be the stability here, with velocities and so on. And the tidal radius, from these definitions, from like the King profile, like the density of stars. So up to which level we have stars that we can consider from the cluster. If the base potential here, either SMC or LMC, is stable, and the orbit of the cluster is stable, everything is relaxed. So the Jacobi radius and the tidal radius are the same, right? So what happens if the LMC and SMC has a close encounter that we know happens, right? So the mass of the potential will increase and the Jacobi radius will shrink. When it happens, there is many of these stars from the cluster that will be outside the Jacobi radius, right? And then when the galaxies move away again, the Jacobi radius will increase back again, and the cluster will be very small, and it will take some time to relax again to fill the Jacobi radius. So we are looking for clusters that just passed this phase, because we know that there was the bridge formation was only 200 million years ago. So of course we have to consider the internal scale of relaxation time of the clusters and so on. But we are looking for that. So what we found is nothing so far. So we are looking for clusters that are underfilling their Jacobi radius, so below this line, the green line. So we are looking for clusters from the first data release, and so far we didn't find any compelling evidence for that, but we'll keep looking. So my take-home message is Magellanic Clouds. They're really important, not only for us, so you understand the assembly of the Milky Way, but also as a test probe for galaxy-galaxy interaction in general. And with resolved stellar populations, we can have the information in 3D, which is amazing. And the star clusters individually, we can have them as a system or individually. So we can have the chemical dynamical evolution, so on, and also even stellar evolution that have projects like B stars and other stellar rotation, many other things that we are currently doing. So just leave this invitation here and open for questions. Thank you.
Sí, gracias, Bruno. ¿Preguntas? Questions? Questions over here?
¿Qué tal, Carlos Román? No, okay, in English. At what point the injection of pristine metal poor gas that you were talking about could help to solve the problem of multiple stellar populations in stellar clusters? I know these are open clusters, not globular clusters, though.
So you mentioned about the pristine gas and the multiple population. So
like, how can this help to understand why do we find multiple populations in clusters? Can this add to that?
Yeah, because, well, the multiple stellar populations in star clusters usually happens because of stellar evolution, right? So there are a couple of attempts to explain that of super fast rotating stars, AGB polluters, and then have first and second generation. So that usually is internal. And then you have to be massive enough to retain this material that's ejected. So that would be related to the total mass of the cluster, I think. But with the infall of metal poor gas, I don't know, because that's just full to build up new star clusters, but I'm not aware of a metallicity dependent multiple populations. For the Milky Way, for the globular cluster, have multiple populations in all metallicities, if I remember correctly.
Thomas?
Yeah, epic work, you know. I really love it. You have calcium triplet metallicities, and you showed the metallicity enrichment history, right? This bimodal infall. Did you ever cross-correlate chemistry with these age metallicity trends that you derive from calcium triplet? Did you ever calculate calcium over iron, for instance, and then see if the second infall is lower in calcium over iron than the first one?
Yeah, for example, from the models for this metallicity dip, they predict some magnesium. At least the magnesium kind of has a shell that's protected from any other internal process of stellar evolution. So that's the one element that we can kind of rely. And there is a loop when you go for metallicity versus alpha or magnesium over iron, but it's very small. So we cannot detect that observationally. So there is, you could see, but what happens is, for example, from the apogee, they have been observing lots of stars in the Magellanic Clouds. And what they realized was that there's a paper called Lazy Giants from David Neidiver. So the idea is that for their mass, because there is this mass metallicity relation of galaxies usually, but the Magellanic Clouds are very massive, but they're not as metal rich as they should be. So there was like not a very efficient in enriching stars. And recently, there was kind of upbending in the metallicity versus alpha. And they relate that, so they cannot prove that this was because of a close interaction, but they say it's consistent. If we think about the new paradigm of the first fall, it's totally consistent with the fall to the Milky Way. So it's kind of boosted the enrichment again.
It would be interesting to do this quantitatively with high resolution spectra at some point.
Definitely.
Yes. Yeah.
Very nice work. I'm wondering if observations are getting to the point in which we will be able to observe an interesting dynamical effect. There's no such a thing as a tidal radius. In reality, it depends on the energy and the orientation of the orbit. For instance, the Coriolis effect stabilizes retrograde orbits, but destabilizes the prograde orbits. So at the end, when you start plucking stars out of the cluster, you end up with a retrograde envelope. And that can give you a lot of information about the details of the tidal field. I wonder if we're getting to that point in which you could try to see if there's rotation in the outer envelope.
I hope. That's the next step. For now, we only have the clusters with spectroscopy from calcium triplet, meaning that we're pinpointing a few RGB stars in clusters that are older than 1.5 billion years. So we still are not in the point of going for Muse, for example, to have a full rotational profile, but that's certainly the next step.
Okay, we don't have more time. Just a quick question. You keep observing clusters, right? Still observing clusters.
Yes.
What's the expected size of the final sample of cluster?
Yeah, good question. We just received approval for a 3 years more extension for observations from, well, that's one thing. So the SOAR telescope, it's a consortium between Brazil, some universities in US, and also the 10% in Chile. So we get access mostly because of Brazil, have 30% there and also 10% in Chile. So from Brazil, we got this long-term project for another 3 years. And I think we'll be done by then. So that will complete 10 years of observations. That's not very efficient because of SOAR, there is no service mode. So it's AO in classical mode. So you can imagine the difficulties with the weather and so on. And just a note for the future. So we keep observing star clusters. We keep with the Gemini follow-up. And personally, also, I'm working on the Sloan 5 with the LVM Rubin Observatory. There will be depth for the halo, the star clusters, and Foremost is coming. So there are many bright future ahead.
Perfecto. Bueno, antes de salir